Okay. Could you tell us a little more about this paper and what exactly you're trying to solve?
Okay, so firstly, though I'm on this paper, my contribution was very modest, and I don't recall all of the details, but I'll try to explain some of the basic ideas or terms. So wait, let's go back to the title. GPU guided speech source separation. Okay, so so source separation is basically if you have two speakers and you want to separate out the audio into speaker A and speaker B. There's also something called source guided speech recognition, which is where you are told somehow which speaker you want to recognize, and the ASR is supposed to just recognize that speaker. So now I don't 100% recall which of these two this paper is about. It might actually be about a kind of combination where there's two loss functions and it's training on both. Let's scroll down a little bit to have a look. Okay. CACGMM. Okay, so MVDR is something that they use in a lot of source separation algorithms. It's called minimum variance directionless response, and basically it's I think that's what it refers to anyway. I think it's basically a way of getting a steering vector that will give you the maximum amount of your signal, let's say speech, and the least amount of noise. And in order to do that, you need some kind of indication of which parts of the signal are like signal and which are noise. So like in the time frequency plot, like that red and yellow and green plot there, those like red lines are like the signal, and the blue part in the background is probably mostly noise. But there could be other sounds in the signal. So normally the way these things are used is that you have a neural net or something that will tell you which time frequency points are mostly signal and which ones are mostly noise. And in some cases that needs to be guided by some kind of let's say a vector that describes the speaker, because let's say if there's a male and a female speaker, like do you want the male one or the female one? There has to be some indication of what it is you want if there's multiple speakers. So basically that time frequency mask is fed into the MVDR beamformer. I don't recall what this CAC GMM thing is. Gaussians are something that GMM probably is Gaussian mixture model, and I think Gaussians are something that appears in the MVDR formulation somehow, so it's probably related to that. So probably what's happening here is okay, let me look at this. Because normally the beamformer is something that happens on the signal level. So that if you have multiple microphones, yeah, there is multiple microphones because it says multi-channel. Then basically you get the steering vector that kind of says the direction in space. And I think I think these steering vectors can be different for different frequency bands. So normally what you do is you then use that steering vector to process the multi-microphone signal into a single low noise signal. Now, I don't know what they're talking about here with inverse STFT. It looks like we're reconstructing a signal from, I think possibly I see what's happening. That maybe we're applying all of this MVDR stuff in frequency space, because the way MVDR is often done, you'll have a different steering vector for each bin. So it's, I think, more for each frequency bin. So it's more convenient to apply it in frequency space. And then the inverse STFT is to reconstruct the actual signal. So then I think this is basically doing denoising. Okay, let's go down. Batch processing for GPU accelerated GS. Okay. So normally when people do these signal processing algorithms like MVDR, or I think GSS is something related. Oh, it's guided source separation, but it uses MVDR. People often use like these slow MATLAB implementations that people at, University of Heidelberg or whatever have created, because these algorithms are a bit tricky, and there are like people have created these implementations, but they tend to be slow. So I think what this paper may be about is a kind of a re-implementation of this on the GPU. Probably it uses PyTorch or something like that. Yeah, WPE is something related to MVDR. It's some popular algorithm for finding the steering vector or something like that. Yeah, let's go down. Multi-channel mix. Yeah, it looks like this algorithm is outputting the signal. There are things that are somehow like this, where you take in multiple channels and you try to do speech recognition directly on top of that, but those are difficult to get them to work. Okay.
Okay, could you explain in really simple terms how you're distinguishing like these two people and what exactly is being transcribed?
Okay, so I don't recall the specifics of the paper, but I'll talk in general about how you do this kind of thing. So in speaker identification, they normally reduce the speaker like qualities to a vector that they might call an I vector or a D vector or an X vector. But it's just a vector that describes the speaker. So normally you can estimate that vector from a short amount of that speaker's speech. So generally speaking, this will be application dependent. So if it's something like Alexa, something like that, the person will say, "Hey Alexa," and then they'll say something, and then you can use the "Hey Alexa" as the kind of prompt, and you can extract your I vector or whatever from that. And if it's multiple people talking, you could just try to find bits of clean speech using a neural net to distinguish clean from combined, and then use segments of clean speech as the I vectors for the to guide the source separation. Yeah, so normally there's some kind of neural net involved in getting the mask that says signal versus noise. And normally the I vector would be some kind of input to that neural net.
Okay, and what's being transcribed when two people are talking at the same time?
Well, ideally what you want is something that says speaker A, and then their transcript, and then speaker B, and then their transcript, and it would have time marks saying when speaker A spoke and when speaker B spoke. And those could potentially be overlapping. In practice, we're not yet really able to do this with any accuracy. But that's how we'd like it to be.
How would you separate the audios when you have the vectors?
When we have the I vectors, we'd input those to a neural net that would give us the time mask for each speaker. And then we'd use the time mask to estimate the steering vectors for MVDR or WPE or whatever it is. And then we'd reconstruct the speech using those steering vectors. So that will give you noticeably purer or cleaner speech. Normally you'd still be able to hear the other speaker in the background, but they would tend to be a lot quieter. It partly depends how many microphones you have and how still the speakers are. This kind of thing works really well on fake data. Like, you know, if you estimate room impulse responses for each of the microphones and then put fake data through it, you know, like put recordings through those impulse responses, it is possible to separate them perfectly. But in reality, speakers are not point sources, and those algorithms don't quite work exactly, but they will give you some separation.
Oh. Do we only want to decode the speaker with the red waves in this diagram?
There are some applications where you just want one speaker, like let's say the Hey Alexa type of application. There's others where you'd want to decode the different speakers. I think this algorithm that's being described in the paper is more generic, and it could be used for either type of application.
Okay, thank you. Bye.
Bye.